Good morning, Mrs. Gates here. Today we are going to talk about orbital motion. In particular, we're going to examine the velocity of objects as they orbit other objects. Perhaps the most famous theories about orbital motion come from Johannes Kepler. His three laws describing elliptical orbits, the way speed changes for orbiting objects, and how orbital radius affects period are still used to describe and predict motions in space. However, it took Isaac Newton to explain why objects orbit with his theory of universal gravitation. Legend says that Newton saw a falling apple and discovered gravity. Now, it wasn't that falling apples were a new idea. Whether or not apples were involved, Newton's realization came not from thinking about falling, but by considering projectiles. In fact, it might be more apt to picture apples being launched from a cannon rather than falling from a tree. Newton's thought experiment went something like this. When you fire an apple from a cannon, it travels in an arc for a certain distance and then lands. If you fire it faster, it goes farther and farther. But what if you launched the apple so fast that it never actually landed, so that the curvature of the Earth and the curvature of the apple's trajectory matched, and the apple kept falling forever without landing? This is what we call orbital motion. Objects in orbit are continuously falling due to gravity, but moving fast enough so that they never land. This is the way the moon orbits the Earth, the way the planets orbit the sun, and the way stars orbit galaxies, constantly falling due to gravity, but never landing. What Newton realized was that the force of gravity not only governs the motion of objects on Earth, but also the motions of heavenly bodies. Newton's law of universal gravitation states that there is an attractive force between all two objects that have mass. This attractive force is proportional to the masses of the two objects and inversely proportional to the square of the distance between them. For objects in orbit, this distance is the radius of their orbit. This law of universal gravitation allows us to calculate the velocity required for an object to be in orbit. To see how this is the case, let us consider a smaller object like a planet in orbit around a larger object like a star. Most planets have an orbital path with low eccentricities, near zero, making them nearly perfect circles. This means that we can treat the planet's orbit like uniform circular motion. Here we know that the net force will be centripetal and can be calculated using the equation mv squared over r, where m is the mass of the object moving in a circle, in this case our planet, v is its velocity, and r is the radial distance. For the case of a planet orbiting a star, this centripetal force is caused by the force of gravity. This gravity is the attractive force between the mass of the star and the mass of the planet. It can be calculated using Newton's law of universal gravitation. The force of gravity equals g times the mass of the planet multiplied by the mass of the star divided by the distance between them squared. As a reminder, capital G is the universal gravitational constant, equal to 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. To find an expression for the orbital velocity, we will set our equation for centripetal force equal to our equation for the universal gravitational force. This gives us an expression that looks like this: mv squared divided by r equals g m1 times m2 divided by r squared. With a little bit of algebra, we can solve this equation for v. Notice that little m is on both sides of our equation and can be canceled. This is the mass of the object in orbit, in this case our planet. Also notice that there is an r on the bottom of both fractions. On the left, we cancel out the radius, and on the right, we cancel out one of the radii squared. This leaves us with an expression of v squared equals gm over r. Our last step in solving is to take the square root of both sides of our equation. This gives us our orbital velocity equation. V equals the square root of gm over r. G is our gravitational constant, m is the mass of the object in the center of the orbit, and r is the orbital radius. Let's consider some predictions of the orbital velocity equation. First, let's consider how the orbital velocity will change if our planet moves farther away from its star. In order to answer this question, consider where the orbital radius is in our orbital velocity equation. Notice that it is on the bottom of the fraction. That means that as the radius gets larger, the velocity will get smaller. Therefore, as the planet moves farther and farther from the star, the orbital velocity decreases. Next, let's consider how the orbital velocity will change if the mass of the star were to increase. Notice that in this case, the mass of the star is the mass in the center of the orbit and is on the top of our fraction. This means that as the mass of the star increases, so will the orbital velocity. However, because there is a square root in our equation, it will not increase in a linear way. Instead, it will increase in a square root curve. Lastly, let's consider how the orbital velocity would change if the mass of the planet or the satellite were to increase. Notice that the only mass in our equation is the mass in the center of the orbit. The mass of the planet is not in our equation. That means that changing the mass of the satellite or the planet will not affect its orbital speed, and the orbital speed will remain constant as the satellite masses increase. The consequence of this is that all objects at the same orbital radius will travel at the same orbital speed, meaning that if you were orbiting in the International Space Station and jumped out, you would continue to orbit with the same orbital velocity as the International Space Station. Lastly, let us consider two numeric examples using our orbital velocity equation. As of 2023, there are an estimated number of over 4,000 satellites in orbit around Earth. The topic of space junk is possibly one for another day, so let's focus on one satellite that we all know and love, the Hubble Space Telescope. The Hubble Space Telescope orbits at a height of 547 kilometers above the surface of the Earth. In order to find its orbital velocity, we don't need its height above the surface of Earth, rather we need its distance to the center of the Earth. If we add the height above the surface of the Earth to the radius of the Earth, we end up with an orbital radius of 6,918,000 meters. We also know the mass of the Earth to be 5.97 times 10 to the 24th kilograms. In order to find our orbital velocity, we will also need the value of the gravitational constant. If we plug these known values into our equation for orbital velocity, we find that the orbital velocity of the Hubble Space Telescope is 7,587 meters per second. In a more familiar unit, that works out to 17,000 miles per hour. How does that compare to other satellites? Well, many GPS satellites orbit at a different height, nearly 20,000 kilometers above the surface of the Earth. That gives them an orbital radius of 26 million meters above the Earth. How will their speed compare to that of the Hubble Space Telescope? Well, consider the orbital velocity equation. Since the GPS satellites have a radius that is much larger than the radius of the Hubble Space Telescope, the bottom of our fraction will increase, and the overall orbital velocity for a GPS satellite will be significantly slower than the orbital velocity for the Hubble Space Telescope.